Hey everybody, it's Monday, March 22nd, and as you can see here in the aim today, our goal for today's video is all about how we can describe the relationship between what we understand about energy and what we understand about springs. Now, before we get to that, I want to take a couple of minutes to review the problem that was posed at the end of the video that was posted on Friday. On Friday, at the end of the video, which was all about springs and Hooke's law specifically, this problem came up on the screen at the end, and I asked you to solve this problem and submit your work for it. It says here a 10 kilogram mass is hanging at rest from a spring with a spring constant of 100 newtons per meter, as shown in the diagram below. And part A of this question says to determine the force acting on the spring, and part B of this question asks to determine the distance the spring is stretched from the equilibrium position. It's very important for everybody to realize in this question that the most important piece of information given in this problem is that this thing is at rest. And the reason why that's the most important piece of information is because that tells you that whatever force is acting downward on this object, which is the force of gravity, is equal to the force that's acting upward on this object, which is the force exerted by the spring. And that really is the key to the first part of this problem, because part A of this question asks you to determine the force acting on the spring, and the force acting on the spring is equal to the weight of this object. And so they tell us here the mass of this object is 10 kilograms. And of course, G is 9.81 meters per second squared. And we're looking for the force that is acting on the spring, which is equal to the force of gravity, which is what we're looking for. And so, of course, all we're really doing here is solving for the weight of a 10 kilogram object. We use the equation that we always use to calculate the weight of an object, Fg equals mg. And so we take the mass of this object, 10 kilograms, we multiply it by the acceleration due to gravity on the surface of the Earth, 9.81 meters per second squared. And of course, when you do that math, it's nice and easy because we're just multiplying it by 10. You move that decimal place over once to the right, and we get 98.1 newtons, of course, because this is a weight. And just to finish this one up, so we're being very obvious about what it is we're doing, we are saying here that the spring force is equal to that weight we just calculated, which is 98.1 newtons. Now, of course, that is just part A. Part B of this question is asking us to determine the distance the spring is stretched from the equilibrium position if, of course, as it says there, if the spring constant is 100 newtons per meter. And so here, that's pretty simple to do. We have K is 100 newtons per meter. We just calculated here that the spring force is 98.1 newtons. And we're looking for the distance the spring is stretched from the equilibrium position, which gets the symbol X in the spring force equation, better known as Hooke's law. That equation, Hooke's law, or the spring force equation, you can refer to it both ways, it's fine, is Fs, the force on the spring, is equal to the product of K, the spring constant, and X, the distance the spring is stretched from the equilibrium position. So to solve this for X, all you have to do is divide both sides of this equation by K. So we get Fs divided by K. And so to solve this here, all we have to do is plug in those numbers. We take our spring force, 98.1 newtons, divided by the spring constant, 100 newtons per meter. Of course, when you do that division, you got to flip and multiply that fraction here with the unit on the bottom. So we end up getting, for the units, newtons times meters over newtons. The newtons cancel, and we end up with newtons, and so that's good. And since we're dividing by 100, all we got to do is move the decimal point back over 2 places to the left. So we get 0.981 meters. And that's it. It's very important to remember for this problem in particular, but for a lot of Hooke's law questions that they actually ask in Regents physics, it's very important to remember that when an object is sitting on a spring and that object is at rest and the spring is hanging vertically, the force of gravity acting downward on that object has to be canceled out by the spring force acting up on that object in order for that object to be in equilibrium. That's the deal. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your solution. And when you hit play, we'll move on. So with that, that brings us to the main point of the video for today, which is all about the relationship between everything we've said about spring so far and everything we've said about energy so far. And really, we can just jump right into this because I think the concept is pretty straightforward. Since a spring is capable of exerting a force, as we just calculated for that last problem, over some displacement, well, that means it's capable of doing work, which means it is capable of storing energy. That, of course, is given by the equation that we have referred to so far as the work-energy theorem. If something is capable of exerting a force and making an object move, then it is capable of doing work. And that means it's capable of storing energy. And that energy, of course, stored energy, and so its potential energy, has a very specific and special kind of name because it's the kind of energy that is stored in a spring. It's called elastic potential energy. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So as we said yesterday, if we were to graph the force that is exerted by a spring over the distance the spring is stretched, it looks like this. And so what we can say from this graph for sure is as x increases, the force increases. And so we have a little bit of a problem on our hands, because if we actually want to calculate the work that's done by the spring, we can't just plug in one number here for F, because that's changing the whole time. It actually depends on how far you've stretched it. And so we're going to take a different approach to coming up with the equation. What I think is important to realize is that in this work equation, you're taking something measured in newtons multiplied by something measured in meters. And if you look at this graph, the y-axis variable is measured in newtons, and oh my God, the x-axis variable is measured in meters. And in order to get Newton times meters, we're doing multiplication. And so ultimately what we're saying here is that when you calculate the area under the curve here, which always involves you in multiplication, the area under the curve will give you the work. And so I'll write here AUC equals W, and I'm going to write it here in parentheses, work. And since work is equal to the change in total energy, that means the area under the curve is going to give us our energy equation. And so if we look at the area under the curve here for this particular triangle, I hope everybody realizes just looking at it, it's a triangle. The area under the curve, the total area, is equal to 1/2 base times height, where the base of this triangle is this distance the spring is stretched from the equilibrium position, x, and the height of the triangle is F with the subscript S, of course, the spring force. And so notice when we do that, we end up getting that the total area is 1/2 x times the spring force. And I hope everybody realizes that that doesn't help us, because the whole point of this was that we couldn't use the work equation because the work equation has the spring force in it, and that is a number that is always changing. And so what we need to do here in order to be able to put this equation in a more manageable form is we need to recognize the fact that the spring force is always given by the equation F equals kx. And so what we can do here with this equation is we can sub in for Fs, the thing that's equal to it, kx, and now we have 1/2 x kx, or in other words, or in another form, I should say, 1/2 kx squared. And that ultimately is how you come up with the equation that we use for elastic potential energy. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So to introduce our equation more formally here, we'll come to this next slide and do it like we always do it. The symbol for the elastic potential energy is PE with the subscript S. Now notice the equation, the symbol we used for gravitational potential energy was PE with the subscript G. Of course, the PE part still stands for potential energy, but since it's gravitational potential energy, we use the subscript G. Here, because we're talking about elastic potential energy, we use the subscript S, really specifically for spring. So that's the symbol for elastic potential energy, PES. The equation, as we just said, is PES equals 1/2 kx squared, where, remember, just like was the case in the spring force equation, K stands for the spring constant measured in units of newtons per meter, and X stands for the distance from the equilibrium position, also measured in meters, just like it was from the spring force equation. And PES, the elastic potential energy, well, it's an energy, so of course it's measured in joules. And so that's what we've written down here. The unit is joules. Remember, the abbreviation for joules is J. And to put that in terms of fundamental units, that would be a kilogram meter squared per second squared. And of course, as is the case for every quantity in this unit, it's a scalar. Energy, work, power, none of those things have direction. And so they're scalars. Take a second to pause this video here and write that down. When you hit play, we'll take a look at how you can use this to solve a problem. Okay, let's take a look at a problem. This problem is from the work energy packet, page 20, number 13. It says a spring with a spring constant of 80 newtons per meter is displaced 0.30 meters from its equilibrium position. The potential energy stored in the spring is. Now, as I hope you'll find as we go through this, these problems aren't that hard. We just took a look at an equation. There are 3 variables in that equation. We're always going to be given 2 of them and asked to solve for the third. They tell us here in this problem that the spring constant K is 80 newtons per meter. They tell us also that the spring is displaced 0.30 meters from its equilibrium position. So that's X. And of course, we're looking for the energy stored in the spring, as the question says, the potential energy stored in the spring is, and so that's our unknown. As we just developed, the equation for the elastic potential energy, the energy stored in the spring, is PES equals 1/2 kx squared, where PES is what we're looking for. And that's good news because the equation is already solved for that. And so we can write here PES equals 1/2 of K, which is 80 newtons per meter, times x squared, 0.30 meters squared. And when you do that math, punching this in here, you take 0.3 squared, that's 0.09 times 80 over 2, you end up getting 3.6 joules, making the answer choice 1, I believe. 3.6 joules is choice 1. That's it, really. They offer these kind of problems usually in a pretty straightforward and easy to understand way. So take a second to pause this video here and write that down. And when you hit play, we'll take a look at another one that gets a little more complicated. Okay, so what I'd like to do now is take a look at probably one of the harder versions of this kind of problem that you could ever expect to see. And that looks like this. I think it's important to realize this is not really all that hard. You just got to pay attention for what you're looking at, what you're given, what you're looking for, what equations relate them, etc. This equation here says a spring with a spring constant of 4.0 newtons per meter is compressed by a force of 1.2 newtons. What is the total elastic potential energy stored in this compressed spring? Okay, cool. It doesn't seem that crazy. They're asking for the elastic potential. And the equation is 1/2 kx squared. So what's the problem? It says the spring constant is 4. Okay, so that's K. And it says here the force is 1.2. And we need X. And we don't have it. And so that's our problem, right? I think it's very important for you to remember, if they ever say in the problem it's a spring, there are 2 equations that we've learned in this class that talk about springs. Sometimes you have to use them together. Notice here our big issue with this problem is the thing they're asking us for, PES, requires K and X, but you have K and F. However, the only other equation you know for springs enables you to find x if you have f and k, which is exactly what you have. That's the deal. So this really is just a two-parter. Let's go ahead and write down the notes here. We're told the spring constant K is 4.0 newtons per meter, and we are told the force on the spring is 1.2 newtons, and we are looking for PES. And so the first thing we're going to do here is say we're solving for x. You don't actually have to mark this as an unknown, but I'm just going to do it here so we can all keep track of it. The equation that relates the force K and x is Hooke's law, Fs equals Kx. So solving that for x, we divide both sides by K, which gives us Fs over K, just like we did in that first problem I showed you in this video. And so we take our force, 1.2 newtons, we divide that by our spring constant, 4.0 newtons per meter, and we plug those numbers in and we do that math, we end up with 0.3 meters for our x. That's the first part. And now it's very important to realize we have K, we have x. We're in business for PES now. And so that's really all that needs to be done. We have PES equals 1/2 kx squared. And so we plug in PES equals 1/2 of K, which is 4.0 newtons per meter, times that distance from the equilibrium position that we just calculated, 0.3 meters. We square that. 0.3 squared is 0.09 times 4 over 2 ends up giving you 0.18 joules. Making the answer here, let's just check and make sure it's an answer choice, and of course it is. Making the answer choice 1. Kind of weird in both problems. Spring was stretched or compressed 0.3 meters. Both cases it's choice 1, but that's just how it works out. Pretty cool. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, let's just write a quick note about this kind of problem because I like these. I like them specifically from a test-making perspective. Because when it comes to a test on this topic, I got to give you a test question where you use F equals Kx, and I got to give you a test question where you use PES equals 1/2 Kx squared. And if I can kill two birds with one stone, so to speak, I'm going to do it. So let's write this down. Big note here. When solving for PES, while given the force and either K or X, we must use F equals Kx to solve for the missing variable and then use it to plug into the elastic potential energy formula PES equals 1/2 Kx squared. Notice that is exactly what we just did. Now, before I tell you to pause this and write this down, it should be noted there is an alternate method. Alternatively, we can recognize that if PES equals 1/2 Kx squared, instead of solving for x and then plugging in the number, we can just solve the equation for x and plug that in. So instead of plugging in the number for x, we can plug in the spring force over K. The spring force gets squared, the K gets squared, it cancels that K, and you end up getting 1/2 the spring force squared over K. Either way makes you more comfortable. It's entirely up to you. Take a second to pause this video here and write that down. And when you hit play, we'll move on. I just want to show that really quick because I feel like a lot of people may be confused about that. And it is a pretty cool shortcut. So we'll say here first, the equation for the spring force is Fs equals Kx. So that means we can solve that as x equals Fs over K, right? We've seen that twice now in this video. Instead of plugging the numbers into there and calculating, what I'm saying, to be clear, is we could take the equation 1/2 Kx squared, and instead of plugging the number in there, we can say that's 1/2 K times x squared, where x is Fs over K. Square that. Now notice when we square that, we get 1/2 of K times Fs squared over K squared. K's cancel here, and that leaves me with 1/2 Fs squared over K. And notice that means here you can do 1/2 times the spring force. Notice here I'm just going to go back to show. Remember, the spring force is 1.2, the K is 4. So we could say 1/2 of 1.2 newtons squared over 4 newtons per meter. And when you do that math, 1.2 squared times 1/2 divided by 4, what do you know? You get 0.18 joules. And so both of those methods are identical in terms of the answer they will give you. The only difference, of course, is that substitution trick, which basically saves you a step. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Very quickly before we go here, I want to do 2 quick things. One of the more important things you're going to see on this energy test is that because we've just developed a bunch of new equations in the last couple days, they're going to ask you about what the graphs look like for those equations. We've talked a heck of a lot this year about how you can look at an equation and figure out what the graph looks like. I want you to take a second to pause this video and think about what this graph looks like and try on your own to sketch it. According to the equation, what is the relationship between the elastic potential energy and the elongation of the spring? What does that mean for the shape of the graph? What does that mean for your explanation? Take a second to pause this video here and try that out. When you hit play, we'll go over it. All right, well, looking at our equation here, I'm not going to write down too much of this because I'm going to flip the slide, but looking at our equation, the elastic potential energy, PES, is directly proportional to x squared. And remember, when the variable is in the numerator and it's squared, it should look like that. And notice that's exactly what it looks like. So we'll say here, PES equals 1/2 kx squared. Since PES, the elastic potential energy, is directly proportional to x squared. Remember, the squared is really important there. As x increases, the elastic potential energy stored in the spring increases exponentially. Remember, the exponentially part there is incredibly important. Take a second to pause this video here and write that down. And when you hit play, we'll wrap it up for today. All right, everybody. That is it for new material for today. Very quickly before we go, I want you to try one of these problems on your own. We have said every single thing you need to know about this problem in order for you to answer it successfully. So here it is. It says a 40 Newton force is exerted on a spring, which experiences a displacement of 0.025 meters. The question is how much elastic potential energy is stored in the spring? Well, that's for you to figure out. The solution will be presented in tomorrow's video. So give this one a shot. I look forward to your submission, and I'll see you tomorrow. Have a good one, everybody.